This is not a story about a person. This is a story about something that is larger than any life and any fate, and at the same time smaller than any speck of dust on your palm. About what surrounds us, passes through us, holds us in place, and yet remains almost entirely invisible. I will tell you about a structure that began with faintest fluctuations of density in the earliest universe and unfurled into a web of filaments, nodes, and voids stretching across billions of light years. A story in which the main character is space itself. At stake is our very notion of reality. 95% of everything that exists we do not see, cannot touch, cannot register directly. We know of its existence only by the shadow it casts upon the visible. We know that the galaxy in which we live is held together by an invisible halo, dozens of times heavier than all the stars and gas inside it. We know that space is expanding ever faster, and we do not understand what is driving it. We know that inside stars there work forces unreachable in any earthly laboratory, and that these forces forged all the heavy elements, including those from which our bodies are built. But behind every known fact stands a question for which there is, as yet, no answer. This story is about how ordinary matter and invisible matter together assemble the world, about what will happen if the expansion keeps accelerating, about the boundary past which the light of extinguished stars will never reach a single observer, about what we know and about what we still do not. And you, have you ever thought that of everything in the universe, the visible is almost nothing? That what is accessible to the eye and the telescope is only a thin film upon something far larger? And if so, what matters more, what we see or what holds us? Listen, this story is about that. If matter in the early universe had been spread out evenly, nothing would have arisen. No stars, no planets, no us. But it was not spread out evenly. Why exactly it happened this way is one of the central puzzles of modern cosmology. The question of what compels vast regions of cosmic space to gather into ordered, stable configurations, as if following some hidden program, has become one of the central directions of scientific inquiry. Any attempt to explain the design of the universe inevitably runs into the need to understand why colossal masses of matter take precisely the forms we observe, and not any others. Early theoretical models started from the assumption of a uniform distribution of matter, but later observations revealed something entirely different. A complex hierarchical system stretching from small stellar clusters to giant plateau-like superclusters. Underlying this grand architecture is the interplay between matter and the geometry of spacetime, where the dynamics is set by fluctuations of density that arose in an infinitesimal moment after the primordial expansion. One of the key elements of this picture is the idea that primordial inhomogeneities could have been amplified many times over during inflation. This theory offers an explanation for why the observable region of the universe possesses roughly the same temperature in every direction, despite the fact that in early epochs, distant regions could not exchange energy. According to the inflationary model, microscopic quantum fluctuations, stretched out to astronomical scales, became the seeds of future galaxies. Within this mechanism, a special role is played by understanding how fields govern phase transitions in the energetic landscape of the young universe. Researchers consider the possibility that large-scale structure is not a chance heaping up, but a reflection of the fundamental properties of cosmic space. A gigantic net of filaments and voids, in which galaxies line up along ridges of density and vast, rarefied regions, form a cellular structure. That is what appears before the observer's gaze. Each of the superclusters can stretch across distances measured in billions of light years. The filaments connecting these objects form what is customarily called the cosmic web, and theorists describe it as the outcome of the influence of dark matter. In such models, dark matter serves as the foundation on which ordinary baryonic matter gradually thickens and forms galaxies. Registering it directly is impossible, but its presence unfailingly reveals itself through gravitational attraction. One well-developed hypothesis suggests that dark matter consists of particles that interact extremely weakly and take no part in any electromagnetic processes. And it is exactly this that explains their complete invisibility. Other models allow for more complex constructions, resembling dark atoms, capable of forming their own stable formations, and even separate dark galaxies. Such ideas remain at the level of theoretical discussion, yet they open an entirely new perception of cosmic architecture, in which visible matter may constitute only a negligible fraction of the whole edifice. About 95% of the universe consists of what cannot be seen, touched, or registered directly. We know of its existence only by the shadow it casts upon the visible. Dark energy is opposite in its properties to dark matter. It is exactly what serves as the cause of the accelerated expansion of space, which is registered when studying distant supernovae and analyzing the distribution of the relic radiation. Within the scientific community, there exist many competing hypotheses about the nature of this enigmatic form of energy. Some models consider it an inherent characteristic of empty space itself. Others allow for the existence of a field that changes its intensity over time. There is also the assumption that the accelerated expansion is a consequence of changes in the very geometry of spacetime, rather than of a separate energetic contribution. All these directions are actively developing, since on our understanding of the nature of dark energy depends the possible fate of cosmic evolution. Understanding the structure requires also making sense of why galaxies form groups and clusters, and those in turn unite into formations of an even larger scale. Within one hypothesis, it is allowed that the universe may be fractal on certain scales. This would mean that similar patterns repeat at different levels. From the distribution of stars inside galaxies to the distribution of galaxies themselves within superclusters. This idea has been discussed for several decades, but direct evidence is still lacking, since the fractal structure breaks down on very large scales, where the distribution approaches uniformity. Nevertheless, models with partial fractality retain their interest as an instrument for studying the self-organization of matter under gravity. From a dynamical point of view, the processes by which gas clouds cool have great significance. When the temperature drops to certain values, dense clumps form inside a cloud, from which stars are subsequently born. An important role in this is played by changes in chemical composition. The first generation of stars consisted almost entirely of hydrogen and helium. Their colossal mass drove the rapid pace of their life cycles and the enrichment of the surroundings with heavy elements. This created conditions for the emergence of more complex structures, capable of sustaining stable planetary systems, and simultaneously opened the possibility of tracing the movement of matter across billions of years through a chemical trail. The relic radiation preserves the imprints of processes that took place shortly after the universe emerged from its dense, hot state. The picture we observe today shows negligible temperature variations, traces of primordial fluctuations that became the seeds of future structures. Studying their distribution has allowed the parameters of cosmological models to be refined, including the ratio of densities of ordinary matter, dark matter, and dark energy, which has significantly improved the modeling of the growth of inhomogeneities and helped to understand exactly how the modern face of the cosmos took on its outlines. Also of interest is the hypothesis of multi-structuredness. It proposes to regard our universe as part of a broader system, comprising many interconnected or independent regions, each of which may possess its own physics and its own set of constants. This assumption is tied to attempts to explain the fine-tuning of physical parameters, thanks to which stable atoms, stars, and planets exist. If there is a countless multitude of universes, then ours could have turned out to be one of the few in which the parameters align suitably for long-term evolution of matter. Such ideas remain theoretical for now, yet they stimulate the search for models capable of uniting quantum phenomena and cosmology into a single picture. One more direction is linked with hidden dimensions. String theory considers fundamental particles as vibrations of tiny one-dimensional objects that exist only in multidimensional spaces, whose number of dimensions exceeds the familiar three. Additional dimensions in this case may be compact and curled up to scales inaccessible to observation. If such a model reflects reality, then the distribution of matter and gravity on large scales may depend on the properties of these hidden dimensions. A number of studies allow that curvature inside such compact spaces could have amplified or dampened primordial fluctuations in the early universe. The study of gravitational waves has become a new instrument for analyzing cosmic structure. These oscillations of spacetime, arising from the interaction of gigantic masses, may carry information about events of the earliest epochs. In theory, it is supposed that primordial gravitational waves could be linked to phase transitions or to the interaction of high-energy fields. If their traces can be detected, it will lift the veil over processes that took place long before the first atoms arose. Existing apparatus is still limited in sensitivity, but future projects are able to bring closer the moment when such information will become available. Some cosmological models allow the existence of large-scale anisotropies, arisen from features of the initial state of the universe. That is, the distribution of matter could have had a preferred direction or axis. Such ideas surface in the analysis of the relic radiation, where a number of studies register faint deviations from perfect uniformity. Hypotheses are voiced that these deviations may be explained by motion through a giant structure or by interaction with objects beyond the observable part of the cosmos. These models remain the subject of active discussion since they demand a revision of fundamental assumptions. For understanding the modern universe, data on the rate of expansion are critically important. A question arises as to why observations carried out by different methods yield mismatched values, a phenomenon that has come to be called the Hubble problem. Perhaps the discrepancies are caused by peculiarities of the local distribution of matter. Alternative hypotheses allow the existence of new physical processes that alter the dynamics of the expansion in different epochs. Resolving this problem may lead to a revision of the entire modern cosmological model, since the rate of expansion determines the age of the cosmos, its density, and the possible scenarios of further evolution. The study of structure is not limited to the observable region. Since light has a finite speed, regions whose signal has not yet had time to reach us remain inaccessible. However, theoretical models allow us to extrapolate their probable state. Some hypotheses suppose that the universe is infinite and contains an uncountable number of structures analogous to those observed. Other models allow for finiteness, but with a non-trivial topology. For example, in the form of a space that closes back on itself, and a beam of light could in theory return to its starting point after crossing a huge distance. Such constructions require complex mathematical calculations, and as yet find no confirmation in observations. While scientists search for dark matter in detectors, the galaxies themselves have long since arranged themselves according to its laws. How exactly did these islands in an ocean of emptiness arise? A galaxy is held together by an invisible halo of dark matter, dozens of times more massive than all the stars and gas inside. Take it away, and the disk falls apart. The trajectory of a galaxy's development, and the reason why such complex systems, uniting billions of stars, are able to keep their shape across immense stretches of time, these questions touch the very foundation of our understanding of cosmic processes. Despite the variety of models, each of them strives to explain common tendencies: the formation of disks, the shaping of central regions, interaction with dark matter, and the influence of the intergalactic medium. Modern astronomy views galaxies as dynamic systems in a constant exchange of energy and matter with the surrounding space. Their structure is not static, even if from the outside it appears unchanging. The early universe was a medium in which the first clumps of matter began to unite under the action of gravity, laying the foundation of future galaxies. Heavy elements at that time were almost absent, so the gas cooled more slowly and the processes of star formation ran under conditions of very high density. In such conditions, stars of enormous mass were born, whose life cycles ran swiftly, saturating the surrounding space with heavy elements. This primary differentiation laid down the individual features of every future galactic formation. A galaxy's structure is determined not only by the amount of matter, but by the distribution of angular momentum. According to a number of models, rotation arose as a result of the interaction of primordial clumps with the surroundings. Small inhomogeneities transferred impulse, forcing the clumps to spin. Later, this rotation was amplified by the compression of gas clouds, which led to the formation of disk-like structures. However, not all galaxies possess a pronounced disk. There exist elliptical galaxies with an elongated oval shape in which the stellar components move chaotically. Presumably, such systems may have arisen from powerful collisions of smaller objects. Collisions play a colossal role in the formation of galaxies. Computer modeling shows that the interaction of two large structures leads to significant changes in the dynamics of stellar motion. Gas clouds are compressed, which creates conditions for new bursts of star formation. If the collision occurs between objects of roughly equal mass, the resulting galaxy often takes on an elliptical form. If, however, one object is significantly larger, the smaller one is absorbed and adds mass to the disk structure without destroying it entirely. Such processes can be observed even today. There are known cases in which spiral galaxies gradually pull in small satellite galaxies. In cosmology, the hypothesis has taken hold that the form of a galaxy is determined by the character of the distribution of dark matter. Since its share significantly exceeds the mass of ordinary matter, it is precisely dark matter that sets the depth of the gravitational potential. A model takes shape in which dark matter forms a halo, a spherical region around the visible part of the galaxy. This halo stabilizes the rotation of stars and prevents the disk from breaking apart. Without it, stars on outer orbits would move too fast and fly apart. Observations show that the distribution of speeds does not match what would be expected from the visible matter alone. This became one of the key arguments in favor of the existence of dark matter. The galaxy has formed, but it is not a frozen picture. It lives and changes from within, in processes stretched over billions of years. A galaxy's spiral arms are like a traffic jam. Cars enter and leave, but the jam stays. A galaxy is not a picture, but a living, dynamic organism. Within galaxies, a continuous interaction is going on between stars, gas, and dust. Stars are born, live through their cycles, and return matter to the surrounding space, from where it becomes material for new generations. Intragalactic gas moves under the action of gravity and radiation pressure. And in a number of models, the possibility is considered that a stream of gas is directed into the center of the galaxy, feeding the supermassive black hole. This intensifies the activity of the nucleus and gives rise to powerful jets, streams of energy able to stretch across distances measured in millions of light years. Such active nuclei are able to suppress star formation by heating the surrounding gas and hindering its cooling, whereupon the galaxy passes into a state of reduced stellar activity. In some models, this process is regarded as a self-regulating mechanism, holding the structure in a steady state. This phenomenon is especially significant for elliptical galaxies, where, because of the aging of the stellar population, the processes of star formation are already minimal. Spiral galaxies show different dynamics. Their disks are shot through with arms, regions of heightened density, which represent not clusters of jointly moving stars, but density waves. Stars enter these zones and leave them, like cars that on a highway slow down at a congested stretch and then pick up speed again. Such a model explains the stability of spiral structures over billions of years, and interaction with neighboring galaxies can additionally strengthen the spirality, drawing the coils far beyond the disk. In some galaxies, bar-like structures are observed, elongated regions passing through the center. According to the models, such bars arise from instabilities in the disk and play an important role in redistributing energy and angular momentum, as well as in driving gas toward the central regions, which intensifies the activity of the nucleus. Hypothetically, such structures may appear and disappear over billions of years, turning a galaxy into a truly dynamic system. Of particular scientific value is the study of dwarf galaxies. Despite their small size, they have played a significant role in the evolution of large structures. It is thought that large galaxies formed in part by absorbing a multitude of dwarf systems. Dwarf galaxies themselves stand out by their variety of forms and compositions. Some contain very ancient stars, others show active star formation. Such objects allow us to study processes of the early universe, since they have retained many primordial characteristics. Their interaction with large galaxies gives rise to stellar streams, elongated ribbons of matter detected by modern telescopes. Hypotheses linked with the intergalactic medium show that it plays a significant role in the fate of galaxies. Rarefied gas of intergalactic space exerts a braking effect on moving galaxies. This process is called dynamical friction and leads to a gradual loss of energy and to the approach of objects toward one another. In clusters, such interactions occur constantly, hastening mergers. In addition, hot gas filling the clusters is able to strip interstellar gas from galaxies, depriving them of material for forming new stellar generations. There are models that consider galaxies as open systems, constantly receiving matter from the intergalactic medium. In the early epochs, when space was saturated with gas, such an inflow could have sustained star formation for billions of years. Some observations show that modern galaxies, too, may receive gas from the surrounding space, renewing the disk and sustaining activity. Analysis of the chemical composition of stars in different parts of the galaxy reveals its history. The inner regions are usually rich in heavy elements, which testifies to many succeeding stellar generations, whereas the outer regions contain more of the lighter elements, indicating a slowed pace of star formation. This difference allows the sequence of events in the galactic past to be reconstructed. Of particular interest are galaxies in which not the slightest trace of dark matter is found. The measured speeds of stellar motion do not require the presence of any additional mass. This throws into doubt some elements of the standard model and forces us to consider new scenarios. Perhaps such galaxies formed as a result of collisions that stripped away most of the halo. An alternative hypothesis allows for the existence of different laws of gravity at small accelerations. These ideas continue to be discussed. They open a path to a deeper revision of ideas about the nature of matter and gravity. Now, a zoom deeper to a single star. How is one born and how does it die? It is precisely stars that forged all the heavy elements from which our world is made. A red dwarf will shine longer than the time that has passed since the Big Bang, and longer than the time until most scenarios of the end. A massive star, by contrast, lives for millions of years and explodes so brightly that it is seen from another galaxy. The question of what determines the inner stability of a star and why the processes in its depths are able to sustain a glow across times comparable with the age of the cosmos itself only seems simple on the outside. Behind it stand fundamental mechanisms of the interaction of matter and energy at temperatures and pressures beyond the reach of any direct experiment. Stars are objects in which conditions are realized that are unreachable in any other medium accessible to modern observation. And it is precisely for this reason that studying them opens a path to understanding the behavior of matter at extreme densities and the manifestations of the fundamental forces of nature. Primordial protostars form inside cold molecular clouds, where the density of gas is sufficient for gravitational compression to begin. As the cloud loses energy and contracts, the temperature in the core steadily rises. At a certain moment, the parameters are reached at which hydrogen begins to convert into helium, a process accompanied by the release of a colossal amount of energy. The radiation pressure that arises balances the gravitational compression, establishing what is called hydrostatic equilibrium, the key condition of a star's stable existence. In stars of different masses, these processes run differently. Low-mass stars burn hydrogen at a very low rate, which ensures them colossal lifetimes. Such objects, called red dwarfs, are presumably able to shine for trillions of years, that is, significantly longer than the present age of the observable universe. Their cores remain relatively cool, the probability of explosive processes is minimal, and they themselves pass through their cycle quietly, without bright flashes and powerful ejections of matter. For this reason, red dwarfs are considered the most widespread stellar type in the universe. Stars of greater mass behave in a fundamentally different way. Their cores heat up to values at which the successive synthesis of ever heavier elements becomes possible. Carbon, oxygen, neon, magnesium, silicon, and ultimately, iron. Each such stage is accompanied by a reduction in the available fuel. When the iron limit is reached, further synthesis becomes energetically unfavorable, and the star enters a phase of instability. The inner pressure no longer holds the mass, and the core begins to collapse. The outer layers are shed into space, while the central region contracts to an extremely high density. When iron synthesis stops, the star collapses in fractions of a second. What remains? An object in which the mass of the Sun fits inside a sphere with a radius of only a few dozen kilometers. In a neutron star, a tablespoon of matter would weigh hundreds of millions of tons. There, where ordinary physics ends, quantum exotica begins, states of matter unreachable in earthly laboratories. The mechanism of collapse remains the subject of many hypotheses. Existing models show that when a certain density is reached, electrons cease to hold proton structures, which leads to the formation of neutrons. This reaction is accompanied by the ejection of a huge number of neutrinos, particles that interact extremely weakly and carry away with them a significant share of the energy. It is thought that the flow of neutrinos plays a key role in the mechanism of the explosion, but the precise details of this process are still being debated. Some models suppose that the shock wave that arises in the collapse receives an additional impulse from interaction with the flow of neutrinos. Other hypotheses consider the possibility of the formation of magnetic fields of colossal strength, capable of redistributing energy. The collapse leads to the appearance of compact objects, neutron stars or black holes. Neutron stars represent structures of unbelievable density in which a mass exceeding that of the Sun is concentrated in a region with a radius of only a few dozen kilometers. The internal structure of such objects remains not fully understood. There are hypotheses about the possible existence of exotic phases of matter, quark-gluon plasma, hyperonic matter, or a boson condensate, which cannot be reproduced under earthly conditions. It is precisely for this reason that neutron stars serve as natural laboratories for the study of the fundamental properties of matter. Black holes represent even more extreme objects. Their formation is linked with a situation in which mass is compressed so much that the gravitational field becomes insurmountable. The inner structure is hidden behind the event horizon, and despite the absence of information about what happens inside, mathematical models allow the outer behavior to be described. Space near a black hole is curved so that light is unable to break out beyond a certain region. The study of accretion disks around supermassive black holes at the centers of galaxies gives the possibility of observing the effects of the curvature of space-time at high temperatures and relativistic speeds. Among the stars, there are objects with unusual characteristics. In some cases, stars are registered whose luminosity does not correspond to the expected mass. Not infrequently, these are binary systems, where the exchange of matter between the components alters the customary course of evolution. In close binary systems, a process of mass flowing from one star to another is possible. If one of them is a white dwarf, the accumulation of matter may trigger a thermonuclear flash, a nova. In more extreme cases, there occurs a thermonuclear explosion of the entire object, generating a Type 1a supernova. Such phenomena are of huge importance for cosmology, since they are used for measuring distances at large scales. There are hypotheses about stars of such great mass that their inner structure is formed with the participation of higher-order instabilities. Such objects could have existed in early epochs, when conditions were fundamentally different, and theoretical models allow that the first stellar generations could have exceeded all mass limits observed today. Their existence could have served as a source of the first black holes, which subsequently grew to supermassive sizes at the centers of galaxies. Stellar winds are another important element of stellar evolution. In massive stars, streams of matter leaving the surface can be extremely powerful, leading to a significant reduction of mass over the lifetime and influencing the outcome of the final stage. In some cases, the loss of mass is able to prevent collapse and change the final result. In low-mass stars, the winds are significantly weaker, but their effect on the interstellar medium, the formation of bubble structures and the stimulation of star formation, remains tangible. Pulsating stars show periodic changes of luminosity linked with physical processes in the outer layers. In a number of models, a mechanism is considered in which the ionization of helium leads to the accumulation of energy, subsequent expansion, cooling, and return to the initial state. The cyclicity of these oscillations allows such stars to be used as standard indicators of distance. Their characteristics make it possible to determine distances to galaxies and to refine the parameters of cosmological models. Of particular interest are rapidly rotating stars, whose speed is so great that centrifugal force noticeably alters their shape, making the objects flattened. Rapid rotation may intensify the mixing of matter, influencing the composition of the core and the length of the star's life. There are hypotheses about stellar objects that do not fit into traditional categories, in particular about stars consisting of dark matter or containing a significant share of it. If particles of dark matter are capable of annihilation, such objects could receive energy from these processes alongside thermonuclear reactions. These models have not yet found observational confirmation, but they widen the horizons of understanding of the possible states of matter. The processes of magnetic activity are an important component of stellar dynamics. In a number of stars, powerful flashes are observed, generated by the interaction of magnetic fields and accompanied by ejections of plasma. In low-mass stars, such phenomena often exceed in intensity what we observe on stars of solar type. Magnetic activity affects the atmospheres of surrounding planets, and its study bears directly on the search for worlds potentially suitable for life. Stellar clusters provide a unique possibility for studying the evolution of stars under conditions in which all the objects formed at approximately the same time, which allows the influence of mass and other parameters on their fate to be assessed. Globular clusters are especially valuable, since many of them contain extremely ancient stars. According to a number of hypotheses, they could have formed even before the emergence of the galactic disk, and their age opens a window into the early stages of the universe's development. Some models suppose the existence of objects made of exotic forms of matter, arising under extreme conditions, with densities exceeding those of ordinary neutron stars, including strange matter or other unusual states. Their existence has not been confirmed, but they remain the subject of theoretical interest as possible manifestations of matter in its ultimate states. The direct collapse hypothesis supposes that black holes may form without the explosive process of a supernova. Some massive stars are able to pass directly into the state of a black hole. Such a scenario could have played an important role in the early universe and possibly explains the origin of black holes of intermediate size. The matter that a dying star has cast off settles into protoplanetary disks around new stars. This is how planets are born, how varied they can be. There are planets where metals melt on the surface. There are planets covered by oceans thousands of kilometers deep. There are planets forever drifting in darkness with not a single star nearby. The question of what determines the ability of a planetary system to take on a stable configuration and to preserve its orbits and chemical composition across billions of years has become central in modern astronomy. The steadily growing number of discovered exoplanets and the striking variety of observed worlds show that the conditions of planet formation are significantly broader than was previously supposed. The study of planetary systems allows us to understand why some stars are surrounded by dozens of planet-like objects, while others have only negligible fragments of material, unable to unite into full-fledged bodies. Primordial protoplanetary disks form from clouds of gas and dust left after the star's formation, and they may contain hydrogen, helium, carbon compounds, metals, and silicates. Coagulation goes on inside the disk. Particles collide and fuse, forming ever larger bodies. In the early stages, there are present objects called planetesimals, bodies with a diameter of a few dozen kilometers, whose collisions lead to further growth. The pace of this growth is determined by the density of the material and the character of movement within the disk. There exist several competing models of the formation of planets. According to the accretion model, small particles gradually unite into large structures. An alternative hypothesis considers the possibility of rapid formation of gas giants due to gravitationally unstable compression. The variety of conditions in protoplanetary disks determines the outcome. At a high disk density, giants may arise quickly, whereas at low density, the process stretches out, and the result turns out to be only small, rocky bodies. A planet's position in the system is determined both by the properties of the disk and by processes of migration. Migration allows the existence of hot Jupiters to be explained, gas giants located right up against the star. Their presence at one time puzzled researchers, since traditional models suppose the formation of large planets only at significant distances, where low temperatures allow gas to condense. Today it is considered that such giants formed far from the star and then moved inward through the system under the action of interaction with gas, gravitational resonances, and collisions with other objects. Rocky planets of the inner regions form differently from gas giants. Their growth depends on the ability of matter to withstand high temperatures near the star. Frequent collisions and significant densities lead to the melting of the material, the formation of magma oceans, and the differentiation of structure. Heavy elements sink into the core, while lighter ones form the mantle. This process allows a planet to develop a magnetic field. If the core remains liquid and mobile, and a magnetic field protects the atmosphere from streams of the stellar wind. In the outer regions of the disk, where significantly less energy arrives, icy bodies are widespread. Here, ice giants may form, consisting of water ice, ammonia, methane, and other compounds. At low temperatures, non-standard chemical reactions are possible, giving rise to structures not encountered in warmer zones. Methane snowfields or clathrate formations, stable on the surface of such bodies. The question of the stability of orbits remains one of the key ones. In a planetary system, gravitational interactions are able to change the inclination of orbits, the eccentricity, and the period of revolution, and in systems with several large bodies, the probability of chaotic changes arises. Nevertheless, observations show that many systems preserve stability across enormous stretches of time. Meanwhile, resonances, situations in which periods of revolution stand in a definite numerical ratio, can either stabilize the system or destroy it, amplifying gravitational perturbations. The discovery of exoplanets fundamentally reshaped ideas about the possible conditions on their surfaces. Worlds have been discovered whose temperatures exceed the melting point of metals. Some planets are located so close to their star that their atmospheres gradually evaporate and gas giants lose matter, forming tails resembling those of comets. There are objects that complete a revolution around a star in a period equal to only a few Earth days. In other cases, planets have been registered with orbits strongly deviating from the plane of the disk, which indicates stormy collisions or gravitational encounters with massive objects in the early history of the system. There are hypotheses about worlds covered by deep oceans, forming in zones with an abundance of water and volatile compounds. The pressure at the bottom of such planets may reach values at which water passes into exotic forms of ice, retaining a crystalline structure under huge pressure. Internal heating, driven by radioactive decay, is able to create conditions for the circulation of water and for complex chemical processes. Another class of hypothetical objects, carbide planets, consisting predominantly of carbon. In systems in which the ratio of carbon to oxygen is significantly higher than in the solar system, planets may form with diamond-like mantles and surfaces covered by graphite dust. Water on such bodies may be entirely absent, and the chemistry may develop on the basis of carbon compounds with liquid hydrocarbons on the surface. Some models describe planets in a state of constant tidal interaction with a star. Such bodies are always turned toward it with one side, which creates enormous temperature contrasts between the day and night sides. On the lit side, the surface may form oceans of magma, while the night side is plunged into eternal darkness and cold. Powerful atmospheric flows carry heat between the zones, and at the boundary of the temperature contrasts, unusual chemical structures may arise. Of particular interest are free-floating planets, objects that have left their systems as a result of gravitational interactions. Despite the absence of a star, they are able to preserve internal heat through radioactive decay and the residual heat of formation. In a number of models, it is supposed that beneath a powerful, icy crust of such planets, subsurface oceans may exist, sustaining long-term chemical processes, which are considered as potentially significant from the point of view of conditions where life may exist. The study of the atmospheres of exoplanets is of great importance. Spectroscopic methods allow the chemical composition to be determined, the presence of water, methane, carbon dioxide, and other compounds to be detected, and also the temperature, pressure, and the presence of cloud structures to be revealed. On gas giants, vortex structures are registered, capable of existing for hundreds of years and exerting influence on the distribution of heat. There are models describing unstable atmospheres in which evaporation gradually strips a planet of mass. Finding itself close to a star, an atmosphere may be destroyed in relatively little time, leaving only a rocky core. This process allows for the presence of super-Earths and mini-Neptunes to be explained. Probably many of them are the remnants of former gas giants. Planets with powerful magnetic fields are able to deflect charged particles of the stellar wind and thereby protect their atmosphere. Where magnetic protection is absent, the atmospheric layers are destroyed. The development of methods of observation steadily widens the horizons of the study of planetary systems, urging researchers to advance hypotheses about exotic forms not previously considered by theory. Between these worlds, not emptiness, hundreds of millions of small bodies are flying through it, shards of ancient collisions, ancient ices, and stone fragments, in whose chemistry the history of the very earliest epochs of the solar system's existence is recorded. Asteroids are not just stones. Their chemical composition is a kind of passport of the epoch when the solar system was only forming. Some of them delivered water to Earth, and possibly organic compounds too, from which life later arose. Planetary moons occupy a special place among small bodies. The origin of these objects is varied. Some of them formed together with the planet inside the accretion disk. Others were captured from the outer regions, and their orbits stabilized over time under the action of gravity. There are also satellites that arose from collisions, when large fragments were ejected into space and gradually united into a single body. Earth's moon serves as a characteristic example of such a process. According to the most well-developed model, its origin is linked with a giant collision between a protoplanet and an object whose mass amounted to a significant share of Earth's mass. The details of this event continue to be refined, but the general picture has already taken shape convincingly enough. The moons of the gas giants show striking variety. They may be icy, rocky, or mixed in composition, and may hide beneath the surface oceans of liquid, sustained by tidal heating. Gravitational interactions in the systems of ice giants create mechanical deformations of the satellites, releasing internal heat. It is precisely this process that explains the volcanic activity of some moons. Even in conditions where solar energy is negligibly small, tidal deformations are able to sustain liquid environments beneath a multi-kilometer icy shell, creating an environment potentially suited for long-term chemical processes. One of the most well-studied structures in the solar system is the asteroid belt, located between the orbits of Mars and Jupiter. This region contains an enormous number of objects, numbered in the millions, but the total mass of the entire belt amounts to only a small share of the Moon's mass, which makes it significantly less massive than one might suppose from the number of objects. There exist different hypotheses about the nature of this structure. By one, the belt represents the remains of a planet that never quite formed into a single body. By another, Jupiter, with its powerful gravitational influence, prevented the material from uniting into a larger object. Gravitational resonances with Jupiter and other planets have emptied out certain regions of the belt, leaving characteristic gaps known as the Kirkwood gaps. The chemical composition of asteroids reflects the conditions under which they formed. Rocky bodies consist predominantly of silicates. Metallic ones include iron and nickel, and icy objects of frozen volatile substances. Such variety indicates that the objects arose under different temperature conditions and at different distances from the young sun. Some asteroids probably migrated from other regions of the disk, which allows the movement of matter in the protoplanetary nebula to be traced. A number of bodies have an elongated shape and non-standard rotation, a consequence of past collisions and the long-term action of the Yarkovsky thermal effect, in which radiation from a heated surface creates a weak but steady thrust, capable over millions of years of noticeably altering the orbit. Beyond the orbit of Neptune stretches the Kuiper Belt, a vast region populated by icy bodies, preserved since the early epochs of the solar system's formation. Within this belt are located dwarf planets, including Pluto, whose orbits are often elongated and inclined. Such features are explained by interaction with Neptune. The gravity of this planet in its time drew a portion of the small bodies into resonant zones, forming classes of objects whose periods of revolution stand in a definite ratio with the orbital period of Neptune. These resonant trans-Neptunian objects are valuable evidence of the dynamic evolution of the outer regions of the system. In the intermediate zone, between the orbits of Jupiter and Neptune, there exist objects called centaurs. They are unstable on long timescales and may gradually shift into the inner regions of the system, turning into comets. Their chemical composition is a mixture of ice and rocks, and upon heating, they are able to release gases, forming a weak coma. Still farther out, at distances practically unreachable for direct observation, theorists suppose the existence of the Oort cloud, a spherical region stretching out to enormous distances from the Sun and serving as the source of long-period comets. Comets represent bodies in which ice and dust coexist in varied proportions. On approaching a star, the surface begins to evaporate, and the released gas and dust form a coma, a diffuse envelope around the nucleus, as well as tails, which are always directed away from the Sun. The tails have several components: a dust one, formed by the pressure of solar radiation, and an ion one, arising under the action of the solar wind, which forces the charged particles to line up along the magnetic lines. Cometary nuclei contain organic compounds, frozen gases, and solid particles preserved from the times of the early disk. Analysis of cometary matter allows the chemical conditions of the young solar system to be reconstructed, and comets to be considered as possible deliverers of water and organics onto planets of the terrestrial type, a contribution that could have proved decisive for the appearance of life. An important role in the dynamics of the solar system is played by the interaction of small bodies with the planets. Passing near a large body, a small object may radically change its orbit, moving into the inner regions or, on the contrary, flying out into interstellar space. Analysis of the craters on the surface of the Moon and Mars shows that the number of such collisions was especially great in the early stages of the system's history, confirming the hypothesis of a period of intense bombardment, which could have exerted significant influence on the conditions of planetary surfaces. Among the small bodies, triple systems are encountered, asteroids with 2 satellites, which vividly demonstrate the complexity of gravitational interactions in close encounters. And studying such configurations allows the density and distribution of masses inside these objects to be estimated. Between the stars, space seems absolutely empty, but even it is filled with dust, gas, and molecules of such complexity that they may serve as the building blocks of life, long before any planet appears. In 1 cubic centimeter of interstellar space, there are literally a few atoms, but on the galactic scale, this near vacuum sums up into structures comparable in mass to whole galaxies, and stores organics more complex than amino acids. The question of what makes a rarefied medium, consisting of the smallest particles and gas atoms, so significant for cosmic evolution, seems paradoxical at first. The density of the interstellar medium is so low that in 1 cubic centimeter there may be only a few atoms, and yet it is precisely this structure that influences the motion of light, the formation of stars, the cooling of galactic disks, and the distribution of energy on scales comparable with the sizes of whole galaxies. Its role manifests itself in processes that cannot be reproduced in laboratory conditions because of the colossal spatial and temporal scales. Cosmic dust consists of particles of a size from fractions of a micrometer to a few dozen micrometers, born in the atmospheres of red giants, in the neighborhoods of exploding supernovae, and in the disks of young stars. These particles include graphite, silicate structures, metal oxides, and icy shells. Dust plays a key role in the cooling of molecular clouds. It effectively radiates infrared heat, which allows the cloud to lose energy and contract, launching by this new cycles of star formation. Without this mechanism of cooling, the formation of stars would have been significantly impeded. The interstellar medium exists simultaneously in several phases. The cold phase contains molecular hydrogen and is the main hotbed of the birth of stars. The warm phase includes ionized hydrogen and atomic gases. The hot phase arises where the waves from supernova bursts or other high-energy phenomena have rolled through. All 3 phases are able to coexist within a single region, and the interaction between them generates a complex dynamic. Regions of hot gas expand, dissipating neighboring clouds, or, on the contrary, compressing them and stimulating bursts of star formation. Shock waves, born in the collisions of clouds and in the explosions of supernovae, compress the gas to values at which gravitational contraction becomes inevitable, launching chain reactions of the formation of stellar clusters. A special role in the life of interstellar clouds is played by turbulence. This phenomenon creates inhomogeneities of density that may become hotbeds of new star formation. But the same turbulence is able to destroy the forming structures, not letting the gas grow sufficiently dense. This duality makes turbulence at once a creative and a destructive factor, and the energy feeding it, presumably, comes from the same supernovae. Magnetic fields add additional complexity to this picture. In some cases, they hinder the compression of the gas, creating a pressure comparable to the thermal one. In others, they direct the movement of matter along the lines of force, forming elongated filamentary structures, along which the material for new stars is concentrated. The interstellar medium contains a broad spectrum of organic molecules, whose presence is confirmed by spectroscopic observations. Hydrocarbons, amino acid-like structures, and long chains of organic compounds have been detected in conditions where, it would seem, complex chemistry is impossible. Under the action of ultraviolet radiation, shock waves, and processes of reorganization of chemical bonds, molecules arise whose complexity is comparable with biologically significant compounds. This raises the fundamental question of how universal chemical processes linked with the formation of complex structures are, and whether the presence of such organics in the interstellar medium may indicate a wider spread of the building blocks of life than was previously supposed. Regions near young stars that emit ultraviolet radiation represent photodissociation zones, where the high-energy radiation destroys molecules and alters chemical processes, determining the composition of dust and gas from which new planetary systems will subsequently form. At intergalactic distances, the density of matter is even lower, but observations register between galaxies hot gas, heated to extreme temperatures and spread across enormous distances. Data of the last decades show that a significant share of all the baryons of the universe is concentrated exactly in these rarefied intergalactic structures, and not inside the galaxies themselves. Within some models, such a medium is organized into filaments and nodes, an extension of the cosmic web, providing the flow of matter between galaxies and thereby sustaining the processes of star formation inside them. This space is pierced by yet another stream, particles with an energy unattainable for the best accelerators on Earth. They fly from the most extreme places in the universe, carrying information about processes that cannot be reproduced by any other means. Imagine a tennis ball in flight. Now pack all its kinetic energy into a single proton, a particle a trillion times smaller than an atom. It is precisely such particles that constantly pass through us from the depths of the universe. And to understand their nature is to peer into the most extreme corners of the cosmos. Cosmic radiation represents a stream of charged particles, protons, helium nuclei, electrons, and heavier nuclei, moving through interstellar space at relativistic speeds. The energy of some of these particles surpasses the capacities of any earthly accelerator, and the most extreme of them possess an energy comparable with the energy of a moving tennis ball, compressed into a single elementary particle. Such cases demonstrate how extraordinary the processes of acceleration taking place in the cosmos are. The main mechanism of acceleration is considered to be the interaction of particles with shock waves generated by the explosions of supernovae. A shock wave, propagating through the interstellar medium, creates conditions in which particles can cross the boundary of the shock front many times, receiving a small increment of energy at each crossing. After a multitude of such crossings, a particle picks up a colossal speed. This process, called first-order acceleration, explains a significant share of cosmic radiation of medium energies. However, there exist particles whose energy is so great that standard models do not give a complete explanation of their origin. These ultra-high energy particles, presumably, may be born near supermassive black holes, where the combination of colossal gravitational fields and powerful magnetic structures creates the conditions for acceleration to ultimate energies. Another hypothesis links the limitation of maximum energy with the interaction of particles with the relic radiation during their long journey through space. Magnetic fields that pierce interstellar and intergalactic space bend the trajectories of charged particles, depriving us of the possibility to point directly to the source. Even weak fields over enormous distances significantly deflect the path. In the atmosphere of Earth, these particles collide with molecules of the air, generating cascades of secondary particles. And it is precisely the analysis of such cascades that allows the properties of the primary radiation to be investigated. Besides the charged particles, an important role is played by electromagnetic radiation across the whole range: gamma rays, X-rays, ultraviolet, visible light, infrared, and radio emission carry information about fundamentally different processes, complementing one another where a single range proves powerless. Gamma radiation arises from the interactions of high-energy particles near black holes and in zones of intense magnetic fields. Of particular interest are gamma-ray bursts, brief but extremely bright phenomena observed from other galaxies, which are divided into two types. Short bursts last less than a couple of seconds and are linked with the merging of compact objects, for example, neutron stars. Long bursts continue for tens of seconds and are considered as the result of the collapse of a massive star, forming a black hole in a catastrophic process, which is called a collapsar. X-ray radiation is emitted from hot gas in accretion disks, where the temperature reaches millions of degrees. At such values, atoms are entirely ionized, and colliding electrons and nuclei emit X-ray photons, allowing structures near objects with extreme conditions to be studied. Infrared radiation opens access to cold, hidden from visible light regions of the cosmos, protostellar clouds, and dust-immersed regions where stars are being born. Radio waves arise from the movement of charged particles along spirals along magnetic lines in a process called synchrotron radiation, and carry information about the remnants of supernovae, active galactic nuclei, and relativistic jets, streams of plasma accelerated to near light speeds. These streams stretch across distances measured in hundreds of thousands of light years, forming some of the most grandiose structures in the observable universe. Analysis of synchrotron radiation gives the possibility of reconstructing the configuration of magnetic fields and estimating the density of particles in distant objects. Neutrinos occupy a special place among the messengers from the depths of the universe. Possessing a negligible mass and hardly interacting with matter, they pass unimpeded through any thicknesses of matter, carrying direct information about processes taking place in the depths of stars and near black holes, into places where no photon is able to penetrate. The registration of cosmic neutrinos opens a fundamentally new window of observation, complementing traditional multi-wavelength astronomy. All these processes, from the birth of stars to gamma-ray bursts, are governed by one fundamental force, the one that Einstein described as the curvature of space-time, and that determines the fate of every object in the universe. Gravitational waves are ripples in the very fabric of space, generated by the merging of black holes. In the 21st century, humanity registered them for the first time, and we acquired a new sense. Now we do not only see the universe, but hear it. The question of the nature of gravity goes beyond the simple description of a force of attraction. Even though existing models describe most observable phenomena with high accuracy, understanding of this interaction remains incomplete, especially at large scales, where effects appear that require additional explanation. Gravity shapes orbits, creates density waves, governs the collapse of stars, and sets the evolution of everything that exists in the cosmos, from single particles to superclusters of galaxies. Modern understanding of gravity relies on the general theory of relativity developed by Einstein. According to this model, gravity is not a force in the customary sense, but the curvature of space-time under the action of mass and energy. Objects move along geodesic lines defined by the geometry of this curved space, and this is exactly what explains the deflection of rays of light near massive bodies, the precession of planetary orbits, gravitational lensing, the collapse of stars, and the behavior of black holes. However, the question of whether this model is fundamental or only a good approximation to a deeper theory still remains open. Gravitational lenses have become one of the most powerful instruments for mapping the distribution of mass in the universe. When light passes near a massive object, its trajectory is bent, and this allows galaxies to be observed that would otherwise remain inaccessible, and at the same time the total mass of the lensing object to be measured, including invisible components. Lensing unfailingly reveals that the mass of clusters of galaxies significantly exceeds the mass of all the observable matter, direct evidence of the presence of dark matter. Gravitational waves have opened a fundamentally new era of observational astronomy. These oscillations of spacetime, arising from the interaction of massive bodies, were registered by detectors for the first time in the 21st century and carry information about processes inaccessible by any other method of observation. The merging of black holes, of neutron stars, and other extreme phenomena. Such observations allow theories of gravity to be tested in regimes where the fields are maximally intense. The anomaly of the rotation speeds of galaxies has become one of the main arguments in favor of the existence of dark matter. Stars on the outskirts of galactic disks move significantly faster than would follow from the total mass of the visible matter. Dark matter does not emit, absorb, or scatter light. Its existence is given away only by gravitational action. The proposed models of its nature are varied, from weakly interacting massive particles to dark atoms and macroscopic compact objects. Not a single one of these hypotheses has yet received direct experimental confirmation, and the search is being conducted simultaneously in detectors at deep underground levels, in the data of gamma-ray telescopes, and in the structure of the relic radiation. There are hypotheses about the quantum nature of gravity. The existence is supposed of an elementary particle, the graviton, responsible for the transmission of gravitational interaction. However, detecting it by direct methods is extremely difficult because of the negligible intensity of interaction with detectors. Uniting quantum mechanics and the general theory of relativity remains one of the main unsolved problems of modern physics. Additional sharpness is added to this problem by the mismatch between the vacuum energy predicted theoretically by quantum models and the actually observed acceleration of the expansion of the universe. One of the deepest contradictions of present-day science, for the explanation of which hypotheses have been proposed about hidden mechanisms of compensation or about additional dimensions, where energy can be distributed differently. Dark energy adds yet another dimension to the puzzle of gravity. It is precisely it that causes the accelerated expansion of space, and its nature is still unknown. In some models, it is considered as an inherent property of space itself, in others, as a field changing intensity over time. Some researchers allow that the accelerated expansion may be a consequence of a modification of the laws of gravity on large scales, and not of a separate energetic contribution. Gravitational segregation in systems containing many objects, a process in which more massive bodies over time move to the center and less massive ones retreat to the outskirts, influences the structure of stellar clusters and may lead to the accumulation of compact remnants of stars in the central regions. The interaction of galaxies generates tidal structures, bridges, tails, rings, which are registered by observations and vividly demonstrate the complexity of the dynamics on scales exceeding the sizes of individual galaxies. This same gravity governs the fate of the whole universe. Where is it going? What will happen to it in billions and trillions of years? If dark energy continues to accelerate the expansion, in trillions of years, each galaxy will find itself in absolute solitude, cut off by an event horizon from everything else, plunged into darkness, where the light of extinguished stars will no longer reach a single observer. The large-scale structure of the universe folds into a pattern resembling a net, filaments and nodes, where superclusters of galaxies are concentrated, alternate with vast voids. On average, the distribution of matter tends toward uniformity, but on the scales of individual structures, this uniformity is strongly disturbed. Superclusters unite thousands of galaxies and possess a mass capable of influencing the dynamics of neighboring regions, and the voids between them may reach hundreds of millions of light-years across, containing at the same time only rarefied gas and dark matter. In the relic radiation, cold spots are registered, regions with a slightly lower temperature, which presumably correspond to large voids, and their nature continues to be studied. The expansion of the universe was discovered in the analysis of the spectra of distant galaxies. The farther the object, the greater the speed with which it is receding. This dependence has come to be called Hubble's law. And in modern cosmology, it is one of the supporting observational facts. The rate of expansion, however, has changed over the history of the universe. In the early epochs, it went swiftly, then slowed down under the action of gravity, and later sped up again. And it is exactly this acceleration that is linked with dark energy. A sharp question arises as to why different methods of measuring the rate of expansion yield mismatched values, a phenomenon that is discussed as one of the most important open problems of present-day cosmology. Perhaps the discrepancies are explained by peculiarities of the local distribution of matter, but alternative hypotheses allow the existence of new physical processes that alter the dynamics of expansion in different epochs. Hypotheses about the nature of dark energy are varied. One of the models supposes that it is an inherent property of the vacuum, a constant built into the very geometry of space. Another considers it as a field, changing over time and potentially capable of a different dynamic in different epochs. If the parameters of dark energy evolve, this may radically alter the predictions about the further fate of the universe. Several directions of research are focused on detecting such changes in the data on the relic radiation, in the structure of the large-scale distribution of galaxies, and in the characteristics of distant supernovae. The relic radiation is the most direct window into the early universe. The temperature of this radiation is almost the same in all directions, with negligible fluctuations, whose amplitude was determined by primordial fluctuations that later gave rise to all the observable structures. The study of the anisotropy of the relic radiation makes it possible with high accuracy to determine the parameters of cosmological models, the ratio of densities of ordinary matter, dark matter, and dark energy. In some hypotheses, the possibility is considered that the relic radiation carries imprints of structures located beyond the observable region. If the universe includes regions that have not yet had time to transmit their light to us, their indirect influence may show up on large scales. Three possible scenarios of a further fate are discussed in modern cosmology. If dark energy retains its present properties, the expansion will continue endlessly, and galaxies will move away from one another until interactions become a rarity. In a more dramatic variant, when the acceleration grows, distances will begin to increase faster than the speed of light, which will destroy first the clusters, then the galaxies, and ultimately, even atoms. An alternative possibility allows the slowing of the expansion or a subsequent contraction if the density of matter and energy corresponds to different ratios. In cyclical models, the universe passes through repeating phases of expansion and contraction, and the mechanisms of transition between them are described as an interaction of gravity and quantum processes, although observational confirmations of these cycles have not yet been obtained. The multiverse is one of the most widely discussed hypotheses of modern cosmology. In this concept, our universe is regarded as only one of countless bubbles of space, arising in the process of eternal inflation, the never-ceasing generation of new regions out of the quantum vacuum. Each such bubble may possess its own physical constants and laws, and it is precisely this circumstance that is proposed as an explanation for the fine-tuning of the parameters of our universe. Among the multitude of possible variants, there was found one in which the parameters prove suitable for the long-term existence of stars, atoms, and life. Other hypotheses consider the possibility of hidden, additional dimensions, in which matter and gravity behave differently than in the customary three, which could explain some anomalies observed in the large-scale distribution of structures, though direct observational evidence of additional dimensions does not exist today. Faint deviations from perfect uniformity, registered in the relic radiation, continue to be studied as possible traces of large structures or of anisotropies linked with processes of the very early universe. Some observations register preferred directions in the distribution of galaxies, which may indicate the movement of the visible region through something greater, or the presence of large structures beyond the boundaries of the observable region. These data remain ambiguous and allow both an explanation within the framework of statistical fluctuations and a more radical interpretation. It is precisely in this space between reliable knowledge and bold hypothesis that modern cosmology exists, a science that poses questions reaching beyond any horizon and finds answers that unfailingly give rise to new questions. Please write in the comments how this story felt to you. It really matters to me to understand which of the hypotheses about the fate of the cosmos seem more convincing to you. The one in which the expansion continues and each galaxy is left in solitude, or the one in which the universe someday closes back upon itself? And also tell me, is it easier for you to watch a horizontal video or a vertical one for the phone?